I have given some assignment, and as I have seen, most of you have still not attempted it. So I thought I will attempt myself. Okay. So the first question is this one, question number 11 of the assignment 3, I think. Okay. So this is the question number 11. And in the question, it is given CU tests were conducted on sand. Each sample was brought to a saturated state before shearing. The results when no further change in excess pore water pressure or deviatoric stress occurred are given below. That means these are the failure stresses, obviously. So sigma D is not changing. That means it is failure stress. And excess pore water pressure is also stabilized. So that means it is now shearing at a constant rate, and it is at a state of critical void ratio. So compare the failure line and the shear strength parameters obtained from total stress Mohr circle and effective stress Mohr circle. That is, compare the total strength and the effective strength parameters of the soil. Comment on the consolidation state of the soil. That is afterwards. First of all, let us plot it. So, okay, and if the above sand sample is subjected to an effective confining stress of, that is of course for you to find out. So we will try to just see how to find out the Mohr circle using Excel very easily. Okay, so one thing is you have to keep in mind that this is not an Excel exercise. Okay, this is a soil mechanics course, and we are just trying to use Excel to quickly and efficiently and plot it in a good looking plot, all right, a good looking graph. So that is our main primary objective. Okay, so that is our main primary objectives. So here we have sigma C, sigma D, and pore water pressure. So obviously sigma 3 will be equal to this one. So we can directly copy this and paste it here. Okay, and if you want to copy the format as well, so you can copy the format. So sigma 3 at failure, total sigma 3 at failure will be definitely sigma C, what is applied. Now what is sigma 1? So sigma 1 we know sigma 1 is equal to sigma 3 plus sigma D. So when we did the triaxial test, so you notice that we applied sigma 3 first with the water, or pressure in the water. So sigma 3 is applied on all sides. Apart from that, so we apply sigma D on top, so that will be the reaction at the bottom. So this is additional weight sigma, additional load sigma D, and we have sigma 3. So the sigma 1 here on this plane, and this plane here is sigma 1 is equal to sigma 3 plus sigma D. So what we do is here is equal to sigma 3 plus sigma D. Enter. So that is our sigma 1 at failure. Now obviously these two parameters or these two stresses which have been listed here, this sigma 3 and sigma 1, they are total stress total stress units or values. So what we have to do, we have to minus the pore water pressure from here. We have to subtract the pore water pressure from here. So what I do, so equal to, so sigma 3 minus U. So delta U is this one. So that is the pore water pressure. Enter. So this is the sigma 3F. So we know effective stress is equal to total stress minus pore water pressure. Okay, effective stress equal to total stress minus pore water pressure. So that is what we have done. So effective stress, total stress minus pore water pressure is the effective stress. So enter. So we will just pull it here and pull it down and we get the results. So here you see it is 210, sorry, it will be this one. Okay, so we will pull it down and it will be this minus this, E2 minus D2. So E2 minus D2. So total stress minus pore water pressure is the effective stress. Enter. So that is the effective confining stress, this one. And what is sigma 1 dash? So sigma 1 dash is total sigma 1 minus pore water pressure. Total sigma 1 minus pore water pressure. So that is the sigma 1 dash. So enter. Okay, so now what we have here is, so I have taken the courtesy of already entering the theta values. So this is theta value. Okay, so this is theta. So this is in degree. So we have to convert that into radian because Excel it calculates in terms of radians. So this is equal to radian, right? So radians and this one, enter. Okay, and we just pull it down and we get the results. Okay, this is in radians. Now we know we know so if there is a element and we apply sigma 1 and sigma 3, and there is a plane at an angle of theta, so we know that sigma theta is equal to sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos of twice theta. Yes or no? So this is the, normal stress. Similarly, we also know that the shear stress on the plane will be given by sigma 1 minus sigma 3 by 2 sine of twice theta. Okay, so what we will do is, so we already have the theta value here, okay, in radian. So now we have sigma 3 and sigma 1. So we take the first value, suppose. So we take this set of values. Sorry, this one, sigma 3 and sigma 1. Okay, so control C, and here we paste the values. Okay, so this is sigma 3 and this is sigma 1. So what we do, so equal to, first of all, sigma 1 plus sigma 1 plus sigma 3 divided by 2. So one part we got. Then plus again sigma 1 minus sigma 3 by 2. So the second part we got. Now this we have to multiply it with cos of, so cos of twice of theta. So this is theta, twice of theta. So cos of twice of theta. So here, what are the things that will not change? So this sigma 3 and sigma 1 and sigma 3, they will not change. They has to remain at the same value. So what we will do, we will give dollar sign here. Shift dollar, shift dollar. Similarly, shift dollar, dollar. And here dollar, and here dollar, dollar, dollar. Okay, and into. Okay, so you see, so this is at 0 degree, we have sigma 1. This is the value. So now if you want, you can format, sorry, so this is the sigma 1 value. So now what we do, we pull it, we hold here at this square box, alright, button, and we pull it down, and we get the values of sigma 1, how it will vary. So here you see 210, which is this one, sigma 3. Okay, so sigma 1 to sigma 3, the Mohr circle will draw. Now here, so this is sigma n, normal stress status. Okay, and we now have the shear stress. We have to calculate the shear stress. So what is the shear stress? So we can simply copy this part, Control C, escape, and we put it there, and we put an equal sign here, and cos will change to sine, multiply. So when it is, when the plane is horizontal, okay, when the plane is horizontal, so there is no shear stresses. When the plane is vertical, there is no shear stresses. Okay, so when the plane is horizontal, there is no shear stresses. And when I pull it down, when the plane is vertical, there is no shear stresses here. So this is sigma and tau. Okay, so now what I do, so I insert one chart here. Okay, so select data. So what I do, add, and x value will be normal stresses, and y value will be shear stresses. Okay, okay, and obviously the scale has to be equal, right? So then only it will look like a circle. So this is the first circle, Mohr circle. So you can change the scale here, format axis, if you give, suppose this is 100, this is 0, okay, and this is 400, suppose this is 0, okay. So we have one more cycle. Now let us just keep it aside for a while and we calculate the other ones. Okay. So let us now come to this part. So what I will do, I will shift this. So I need all total of 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, and similarly 6 sets. Okay. So first of all, let us put the total stresses here. Okay, so these are the total stresses. So 233 we have already put. Okay, then we will put 360 and 612. So this will be here. So paste total stress. Then Control C. So here we put total stress. Okay, then we put the effective stresses. So here, corresponding to this set of total stress, we have this effective stress. So Control C, and we have this one. Okay, effective stress. And here we put this one, and here we put this one. Okay. So what I do is, first of all, here I copy this. Okay, but when I copy it, you will see this will not change. Okay, so I have to pull it here. And these are the values. So I will, so these are sigma n dash. And obviously tau dash and tau, they are same. So if I, even if I put a tau dash here, there is, I mean, not a big deal because effective shear is, I mean, unchanged. Alright, so shear is unchanged in total and effective stresses. So I pull it down. So I pull it down. Okay, sorry, what mistake I made. Okay, this came here. Okay, so it should be here. Alright, so now again let us plot this Mohr cycle. So select data, add X will be this one, okay, Y is this one. Some mistake I made. I think I have not changed the angle here also in case of this one. So here you see I have not changed, so this is a mistake. Okay, so I change it to K5 here and enter, right, and I pull it down and I get the Mohr cycle automatic. Alright, so you can see the difference. So this is the total stress Mohr cycle and this is the effective stress Mohr cycle. Okay, so similarly what I do, so I will just copy this here and I have to first correct the things. So if I copy it, so this will move here. So this has to be corrected. So angle has to be corrected. You can just pull it there and correct it. Okay, so angle is corrected. Here, first angle, correct the angle. Okay, so for this one, this will be sigma 1, enter, and this will be sigma 3, total stress, enter. And similarly, this will be sigma 1 and this will be sigma 3, enter. And here also we have to change it. So this will be sigma 1 dash and sigma 3 dash, enter. And similarly tau dash here, tau dash and tau are same. Basically we can, I mean, even if we do not change, it will be same. Alright, so enter. So here you see tau and tau dash, they are unchanged. So pore water pressure has no effect on the shear stresses. Okay, so similarly let us again control C and control V. So first of all we have to change the angle here, enter. Okay, then we have to change the total stresses. So total stress sigma 1 F will be this one, sigma 3 F will be this one, enter. Similarly sigma 1 F will be this one and sigma 3 F will be this one, enter. And here also sigma 1 dash F will be this one, sigma 1 dash will be this one, sigma 3 F will be this one, enter. And here sigma 1 dash will be this one, sigma 3 dash will be this one. Now what I can do is I can select all of this and just pull it down, and all the data will be calculated. Okay, so now let us add one by one. So first I will add select data. So these two sets are already done, so I will add these two sets. Okay, so X will be the normal stress, okay, and Y will be the shear stress. So it went outside. Let us check what is the maximum value of the normal stress. So it is 1133. All right, so 1200 will do. So we do this, so we change it to 1200. Okay, and similarly what we do, we change it to suppose 600. Okay, it is, we change it to 500. Let us see. No, 400. Okay, let it remain 600 or 500, let it remain. We will pull it a little bit. Okay. So this one is done. So this set is entered. So now what we do, we enter this select data. So we will enter this effective stress. Okay, again X here. So here you see again the same thing is happening here. So this is the total stress minus the pore water pressure, we have the effective stress. So this is the total stress minus the pore water pressure, we have the effective stress. Okay, and we will now plot the last set. So add, so this will be the x-axis normal stress and shear stress will be the y-axis. Okay, and similarly we will add it here also the other set. So this will be effective stress, normal effective stress, and this is the shear stress, same thing. Okay. So what I can do is I can now move chart to a new sheet. So here we have three sets of effective stress Mohr circle and three total stress. Okay, so now we will plot the total stress shear strength parameters and the effective stress shear strength parameters. So how to do that? So here we have C and phi. Okay, and normal stress and this shear stress. Okay, so first of all what we are going to do, we are going to assume some normal stress values. We are going to assume some normal stress values. Okay, so normal stress values we can assume, so up to the maximum value of this is 1133, so we can assume 0, 50 and likewise. Okay, so format we can change and we can pull it down. Alright, so up to 1400 we can take. So this is the normal stress values. Okay, x values. Okay, x values. Now we have to calculate the shear strength. So what is the shear strength? We know tau is equal to C plus sigma n tan of phi. So easy. Okay, so what we are going to do here, so C we are going to suppose take a value, maybe let us take 0 because we will start with some value. Alright, so if it is not 0 we will see, and phi we take a value, suppose 30 degree. Alright, so this is CCU, that is we are going to find out what is the total strength parameters. Okay, so neglecting the pore water pressure, and we are going to plot the failure line through the total stress Mohr circle. Alright, tangent to the total stress Mohr circle, and then we are also going to find out what is the effective stress parameters. Okay, so here now what we have to do is, so C which is equal to C, so let us first give the dollar sign so that it does not change, C plus sigma n. Now what is sigma n? These are sigma n values. So these are sigma n values. Okay, these are sigma n values. This line, sigma n into tan of, now remember if I give 30 here, you have to convert that into radian. Okay, so if I give 30, that will not be, that will, I mean Excel will take 30 radian, so we have to convert that into radian. Okay, 30 degree, so convert degrees to radians. Okay, so radian. Okay, then 30, then we need not change this, so we will again give a dollar sign. Okay, and this is sigma and tan of phi, and this is C plus sigma and tan of phi. Enter. What mistake did I make? Oh, there will be another this one. Okay, so enter. Yeah. So let us plot it. So I will come to this chart, select data, add. X-axis will be the normal stresses, y-axis will be the shear stresses. Okay, so obviously it is way too big. So here what I can do, I can decrease the phi value. Alright, so there are options for also doing numerical calculations within this Excel, but that we will see later on, because today our main emphasis is to understand what is the effective stress Mohr cycle, what is the total stress Mohr cycle, and how to find out the correlation between the what is the correlation between the two, and what is the shear strength parameters. Okay, so that is the thing. So here we will increase 22, maybe. Let us see. Yeah, so it is almost, so 23. So yeah, it is almost tangential. Okay, so if I give certain amount of C and this is 22, let us see. Yeah, it is accurately giving the plot, right? Accurately tangential. So this is the effective stress. Oh, sorry, this should be what? This should be total stress. Okay, so I made a mistake. So this will be here. Okay, we can also change that. So what we will do, we will control C here, control V, and first of all we have to change this. So we have to bring it here. Okay, and 5 and 22. Okay, so control C, control V, and we can pull it down, and here we can pull it down as well. Okay, so this is, so let us plot this one as well. So chart, we will plot, select chart, add x-axis. So we will select this one as the x-axis, and we will select this one as the y-axis, and okay. So now what we will do, we will change this. So definitely this will be way less. So maybe let us take 15. Okay, so yeah, it is here, you see. Okay, it is changed now. So a little bit less, 14 degree maybe. Okay, so it is giving us almost comparable results. All right, so this is the total stress envelope. Okay, considering the total stress, and this is the effective stress. Obviously, when we define shear strength parameters of a soil, we should always take the effective stress parameters. Okay, and we should uh, I mean either observe, measure, or at least estimate what will be the pore water pressure generation there, and then we should do the analysis, whatever analysis we need to do. Okay, as far as possible, we should always take the effective stress parameter. Okay, in certain cases, of course, like when there is a significant amount of shearing, very quick shearing, all right, and the case is undrained, so we may go for looking into that aspect. So if the stability is really, I mean, we have to be, we have to take precautions if there is certain, such kind of situation arising where there is a shearing at a very quick rate, and there is certain significant amount of pore pressure generation, and it is undrained shearing at all right, totally it is undrained shearing. So in that cases we may need to consider. So here you can see, so this is the Mohr cycle. So these are the total stress Mohr cycle, and we have the effective stress Mohr cycle. So only thing is that we have subtracted the pore water pressure, it has moved to the left. So this circle moves to the left as soon as I consider the pore water pressure. So that is the effect. So very easy to do. Okay. So similarly, here we have the second this example. So example number 12. So it is given axial strain and sigma df and this one. So plot the deviatoric stress versus axial strain. So first of all, insert, plot, select data, add deviatoric stress versus axial strain. So x-axis will be axial strain, okay, and y-axis will be deviatoric stress. So this is the stress strain plot. Then what it is given? Excess pore water pressure against axial stress, axial strain. Okay, so we again insert one more plot. So excess pore water pressure, sorry, x will be this one, axial strain. Okay, sorry. So delete. X will be axial strain and y will be pore water pressure. So pore water pressure is also increasing. Okay, so it is a normally consolidated soil. We can easily say that. Pore water pressure is also increasing, and it got stabilized at a particular value. Then what is the thing? Total stress path as P and against Q with effective stress path as P against P dash on the same plot. Compare and explain the reason. Alright. So reason you have to explain. So P and Q. So how to find that out? So before finding out P and Q, we have to find out what is sigma 1 and sigma 3. Okay. So what is sigma 1? So let us copy this one, C and P here. So this is sigma 3 first of all. So sigma 3 is obviously equal to this one. Alright, so we need not do that. So sigma 1. This is not failure, okay? So this is sigma D increasing. This is not failure. Sorry, I just copied it so it remained there. So sigma 1. So what is sigma 1? So sigma 1 is equal to sigma cell. So this is sigma cell. Alright, cell pressure that is. So we can consider that to be sigma 3 total. That is the total stress sigma 3. Okay. And the hydrostatic pore water pressure is also there, 150 kPa. Alright, so we have to take into consideration that one as well. So sigma 1 plus sigma D. Right, so initially it is at the point. So we can copy the format. And here this should not change. So we will fix the cell. Okay, enter. And it is done. Sigma 1 is calculated. Okay, so what is now P? What is P? So we know for axisymmetric condition, so we have a triaxial cell like this. triaxial element we have axisymmetric condition. Okay, so sigma 3 is radially applied in all direction. So sigma 3 and we have sigma 1 from top. Okay, for that condition P is given by sigma 3 sigma 1 plus twice of sigma 3. Alright, so sigma 3 in x direction, sigma 3 in y direction. So this is y direction and this is sigma 3 in x direction. Okay, twice of sigma 3 by 3. So that is P. What is Q? Q is sigma 1 minus sigma 3. Basically it is equal to sigma D. That is Q. So this is itself Q. Okay, so we have to calculate P. So P is equal to sigma 3 plus twice of sigma sigma, this will be 1, right? So sigma 1 twice of sigma 3 divided by 3. Okay, divided by 3. Now here this I do not want to change, sigma C1, that is C1 I do not want to change, so I will put the dollar sign there and enter. So I can copy the format here. So this will be 400. So sigma 1 and sigma P and sigma 3 all are at the 400 point. Alright, total stress. So I will just pull it down and it is done, calculated. P is calculated at various points. Okay. Now I have to calculate P dash. So what is P dash? So P, insert symbol and dash, insert. Okay. So what is P dash? P dash is equal to this minus, now when I say P dash, so P dash is equal to P minus U. Okay, P minus U. So that you have to keep in mind. So it is P minus U. So U means the total pore water pressure, whatever it is there, whatever was our hydrostatic pore water pressure or the back pressure, whatever we say. So hydrostatic pore water pressure or the back pressure. Alright, so whatever you say that, so that is 150 kPa. It is already there within the soil. Apart from that, when we shear the sample, there will be increase in the pore water pressure. So it will be delta U plus delta U. Alright, so we have to subtract everything from P. So then only I will get the effective stress, confining. Alright, effective confining stress. So P4 minus, I can say this one first, that is the hydrostatic pore water pressure, minus again the excess pore water pressure. So obviously this will remain unchanged. So here C2 I will put dollar sign here. Okay, and enter. So you can see it is 250. So that is actually the effective stress, effective confinement there. And I will pull it down. Now what I will do, I will plot it. So these two plots are there already. So this is pore water pressure versus strain, and this is the deviatoric stress. Okay, and now what we are going to do, we are going to insert one more and plot the stress path. So now first of all select data and add. So let us first plot the total stress. So P will be in the x-axis, so P versus Q. So Q, as we know, it is sigma D, whatever it is applied. So we will consider this sigma D. Oh, see, it is straight line, and the gradient of the line is 1 is to 1 by 3. All right. So already that has been discussed in detail in the class. Okay. Now let us plot the effective stress path. Select data, add. Now this is P dash and this is Q. Oh, you can see it took a different path. Why? Because this is the pore pressure generation here. Okay, and you see it came down. All right, it came down here. So why it came down, we have already discussed in the previous classes. So just look into the this one. So now let us see the effect of the pore water pressure. If I say that the hydrostatic pore water pressure is 100, oh, the effective stress path just shifted to the right. Now if it is 0, let us see what happens. Oh, it started from the same point. Okay, so this is the effective stress path and this is the total stress path, and ultimately you see it failed at that point. Okay, so this is the maximum deviatoric stress it can take, so it is actually dependent on this path, not the total stress. Okay, it is dependent on this path. So the effective stress actually governs the behavior of the soil. Okay, so that you have to keep in mind. Apart from that, here have I given no, I have not given Mohr Coulomb envelope. Okay, we will do that in the next calculations. So this is the stress path here. So now if I give 50, is shifted, 100 shifted. Okay, but thing is that here I have taken a certain data and I've just plotted it. Now if the effective stress is really different, then this entire effective stress will be different. Okay, the behavior of the soil is related to the effective stress of the soil. It will not be when we do an actual test and I change the hydrostatic pore water pressure. All right, initial effective stress will change. So in that case, the entire behavior of the soil will be different. I am just showing you mathematically what is happening. All right, so but in actual case, if I do the test of a sample, it will not be like this. All right, so in case of 300, it will be a little bit more. It will go a little bit more. All right, in case of uh, this is 150. All right, so this is exactly for the 150 value. All right, so this is what is happening. If I increase it more, 200, so the total stress will actually decrease. It will fail somewhere here. All right, in this manner. In this manner, it will fail. Okay, so we will see that when we see actual data of the soil and actual plots, we will see how the things behave. So I just want you to get an idea of the things. So this is for the 150. This data is for this configuration only. All right, so that is total stress path and effective stress path. Then this is the pore water pressure development with strain. Okay, and this is the deviatoric stress with strain. Now let us see the question number 13. Okay, so what is given in the question number 13? So we have Cu is equal, the Cu triaxial test was conducted on isotropically consolidated silty clay with effective confinement of 125 kPa. Test data is given below. Alright, so we have the pore water pressure and these things. So we have to plot the Mohr circle stress path as well. So first of all, what I do, I simply copy this, Control C and Control V, and it is calculated automatically. Okay, so it is calculated automatically. Sigma 1 is sigma C1 plus this one. Okay, C4, enter. So this is the total stress, sigma 1, definitely equal to this one. This is not failure again, okay, sorry, this is sigma D. Okay. So we just pull it down, we can pull it down, no problem. So we got the final value as well. Alright, P is already calculated. So this SP is already calculated, and we have P dash, so already calculated. So total confinement minus this I mean whatever confinement this hydrostatic pore water pressure is there, minus the excess pore water pressure, so that is already being done. Okay, so I can just pull it down, I can get the data. So now we have to plot the Mohr circle. So what I do, I copy this set. So total of how many Mohr circle will be there? So 1, 2, 3, 4. Okay, and we have to plot it for the effective and the total stress as well. So definitely 1, 2, 3, and another we will require. Okay, so what I will do, I will copy this entire thing. And I will paste it here. Okay, and the calculation is already there. Now I will change the values here. So sigma 1, sorry, this will not be F here, so this we can change. So sigma 3 total, it will be always 275. Okay, so for all the cases it will always be 275. So I will just Control C and paste value, and here paste value, and here paste value. Okay, so that is done. Now apart from that, what we have to do is we have to calculate what is the sigma 1. Now sigma 1, it is given for first of all 0.05. So 0.05 for this one. Okay, so for this one sigma 1 is 280. So this one, so Control C. Okay, and we just paste Control V. Okay, then we have for 0.56. So okay, is this not for this one? I think I made some mistake. Oh, okay, this here, it is here 0.56. Okay, so 0.56, where it is? Yeah, this one, this one. So total stress is 310 sigma 1 at that point, at that strain level. So we will plot it here. So sigma 3 and sigma 1 it is done, so sigma 3 we will plot it here. Okay, so we can give one, sorry, merge text. So this will be for 0.05 strain. Okay, so format here. So this control fee, so this will be 0.56, just to be sure. Okay, then we have control C, control P, so this will be how much? 2.43, so this will be 2.43, 2.43, 2.43. Then we will have another set here, so control C, control V. Okay, so this will be how much? 9.15, so this will be 9.15. Okay, so obviously this will be remain same. All right, so 275, 275, 275 and 275, that will remain same. Sigma 1 will be 281 corresponding to 0.05, that is 280.5. Then 0.56, 310 we have already copied. 2.43 it will be 360. Control C, it will be, this will be 360, paste. And for 9.15 it will be 395.5.8, so that control C here and this is control V here, paste values. So total stresses are input, total stresses are input done, input done. Okay, so now we have to input the this if effective stresses. So sigma 3 will be 125. Control C, paste value. Then I have to calculate sigma 1 dash now. Okay, so I will just put it one more here. So this will be sigma 1 dash. Okay, so what is sigma 1 dash? Is equal to sigma 1 minus, same thing, pore water pressure minus the excess pore water pressure. So hydrostatic pore water pressure will remain there, so this one will remain there, so enter. Okay, so it is, you can see it is same as P dash at the start. Okay, but it will be slightly different from P dash as we go up. All right, so 0.05 it is 126.5, so control C, so we will paste it here, paste values. Okay, then 0.56, control C, so here you see it almost dropped to 0. Okay, so it almost dropped to 0 and then it dilated again. Alright, so the pore water pressure got reduced. Alright, so pore water pressure increased here and then it decreased. Okay, so you can see that. So a really interesting problem here. So sigma 1 we have 0.56 we have plotted, so we can plot this one 2.43, control C here. Okay, 2.43 paste values. Okay, then we have for 9.15, control C and paste. Okay, so then we will change this one, so this will be 0 here. So the calculation is done, and we will plot it in the next class. Okay, so the calculation is already done, we will plot it in the next class. So today we will stop here. So only thing is that these are the equations, very simple, on we have to calculate them at the different steps. At the different steps we have to calculate, and obviously we will definitely plot it in the class itself, and we will do that tomorrow. Okay, so we will stop here.